Okay, so this video is on the area under a curve. The two big ideas in calculus are the tangent line problem and the area problem. The tangent line problem dealt with derivatives and finding the slope of the tangent line at any point on a curve. Well, now we're going to look at finding the area under a curve using integration. So a basic overview of areas as limits. In the limit of rectangles, we take the area under the curve on some interval by approximating a collection of inscribed or circumscribed rectangles in such a way that the more rectangles you use, the better the approximation for the area. And finally, the number of rectangles, as it increases without limit, then this will give us our area, which is also known as integration. So for now, we're going to be looking at the area of a region bounded by the x-axis, the graph of a function that's non-negative, meaning it stays positive, and it's defined on some interval. On Friday, we had talked about the foldable that we were working on had a left sum, a right sum, and a midpoint sum, and these are three types of Riemann sums which deal with rectangles, approximating rectangles underneath of a curve, finding their area, and that's how you find the area underneath of a curve. So you have the left one, which is your lower sum, the right one, which is your upper sum, and the midpoint, which is the average. And then you have the legit definition for a definite integral. You have a function which is continuous on an interval. The function is positive for all those x's in that interval. And then you take your interval, you break it into subintervals of equal length, and then the definite integral over the definite integral of f over that function is given by this here. Remember that this gigantic E stands for the summation, which is the sum, and this is taking the limit as n approaches infinity of the sum of the rectangles, which is equal to the integral from a lower limit to an upper limit of the function. So in other words, let's look at the general solution method for inscribed or circumscribed rectangles, finding lower or upper sums. You draw a rough graph of the function over the interval. You use the formula delta x is equal to your top interval minus your lower interval over n to determine how you're going to find these subinterval lengths. You find your heights of the rectangles at either the left end or the right end, and then you find the areas of the rectangles and you add them up, which is what we had done on the foldable. But let's do some more examples, just so that we can really get a good foundation as to what we're doing. So now let's look at example 1. Approximate the area under the curve of y equals 2x minus 3 above the interval 2 to 5 by dividing the interval 2 to 5 into n equals 3 subintervals of equal length and computing the sum of the areas of the inscribed rectangles, meaning they want us to find the lower sums. So very first step we're going to do is we draw out the function, which is a linear function with a y-intercept of -3 and a slope of 2. Pretty basic, which is what we have here. And we want it on the interval from 2 to 5. So we've got that here. Very first thing we got to do is find the width of our rectangle. So we take our interval and divide it by the value of subintervals that are needed. So 5 minus 2 divided by 3 gives us 1. So on the graph, we're looking at the interval from 2 to 5, and we notice that if we need 3 rectangles, well, each of them is going to have a width or a base of 1. So then we just, since we're going lower sums, we can start from the left-hand side. So we go up from 2, figure out its intersection with the line, draw in our rectangle. We go from 3 up to the function, find its intersection, draw in that rectangle. And then at 4, where does it intersect with the function? Draw it over. So you've got 3 rectangles. The height of this first one is 1, the height of this second one is 3, and the height of the last one is 5, each with a base of 1. Well, 1 isn't really going to make a difference to find our areas, so 1 times 1 will give us 1. I'll put a little 1 in there. Can't really see it. Put it on top. Base of 1, a height of 3, and then a base of 1 and a height of 5. So to find the area underneath this curve, we take the areas of the rectangles. So 1 plus 3 plus 5, which gives us an area of 9 units. That should be squared. We're talking about areas. So let's do another example. Approximate the area under the curve of y is equal to 5 minus x squared above the interval from 0 to 2 by dividing the interval into 5 subintervals of equal length using circumscribed rectangles. Well, circumscribed means on the outer part. So really they're talking about upper rectangles or a right sum, which we have here circumscribed meaning overestimates. Before we start drawing anything in though, we need to find our intervals. So we're going from 0 to 2 with 5 subintervals. So 2 minus 0 divided by 5. So each base, each width has to be 2/5. So we're going to be going from 0 to 2/5, 2/5 to 4/5, 4/5 to 6/5, 6/5 to 8/5, and then finally 8/5 to 2. And that'll give us 1, 2, 3, 4, 5 subintervals, which is what we have on this graph down here. And they asked for right ones, so you go from the right hand side first. And these should actually be going from the right. So we should have them here, here, here. Let me just make sure. They started from the left. So they went this way, this way, this way, this way, and this way. So 1, 2, 3, 4, 5. They're all within that interval that they asked us for. Now, rather than trying to calculate it off of the graph, you were given the function, 5 minus x squared. All you need to do at this point is plug in the values from the subintervals into the function to find out the heights. So f of 0 gave us 5, f of 2/5 gave us 121 over 25, f of 4/5 gave us 109 over 25, and so on and so forth. So to find the area for these rectangles, find the area of each rectangle and add them up. Well, they all have a base of 2/5 in between, so we can factor out the 2/5. They all have a denominator of 25, except this first one, so change it into a fraction and add them up. So 125, 121, 109, 89, and 61, all of it divided by 25. You end up with 505 over 25 times the 2/5 that was on the outside. Distribute that in, gives you this, and then simplify this into 8.08 units squared. Another example. Find the area under the graph of this function on the interval from 0 to 5 with n inscribed rectangles. Inscribed meaning lower sums or underestimates. Before you do anything, find your delta x, find your intervals first. So 5 minus 0 divided by 5 gives us 1, which is pretty nice. So we're going to have on our graph is a linear function with 5 rectangles underneath it, and of course here again we're given a function. Plug in your intervals into the function to find your heights. So f of 0 is 1, f of 1 is 1.5, and so on and so forth. Find the total area, you add up the area of the rectangles. Each had a base of 1, so 1 on the outside, the heights of each one on the inside. Add up the inside, multiply by the outside, so our total area here is 10 units squared. Now, we had talked about this on Friday when we were working on the interval. As you're going through the process, several things should become apparent to you. Drawing the function is not really necessary because you're given the function and really you're just plugging in values into the function. The more rectangles you create, the more work you have to do. However, the more rectangles you have, the more accurate your area will be. But it is a lot of arithmetic. And in each case, the base is the same, which allows you to factor it out. And the only difference between a left end and a right end sum is the first and the last height. So, I think we have 2 more examples that we have to do. Okay. Find the area A under the graph of the given function on the interval from 0 to 3 using the midpoint heights and n equals 6. So first find those intervals. So 3 minus 0 divided by 6 gives us half. So our intervals will be 0, half, 1, 1.5, 2, 2.5, and then 3. But they're asking us to use midpoint heights. So we're going to use, rather than half, we're going to cut it in half again to find the midpoint values. So 1/4, 3/4, 5/4, 7/4, 9/4, and lastly 11/4. And that's going to be the heights for our rectangles. So to find the heights, we're going to plug in those intervals into our given function, which is what we have here. And lastly, just like we've done before, to find the total area, our change in x, which is our base intervals, times the height of each of the rectangles. Well, our change in the intervals is 0.5. If we add up all the heights, that gives us 18.125. Multiply the 2 gives us an area of 9.0625. One more example. The table below represents the velocity in feet per second of a car traveling on a straight road. Approximate the integral from 0 to 50 of the velocity function with a Riemann sum using the midpoints of 5 subintervals of equal length. So they gave us the table from 0 to 50. They want 5 subintervals. So if we take 50 minus 0 and divide it by 5, that gives us an interval length of 10. So our very first interval will be from 0 to 10. The next one will be from 10 to 20, 20 to 30, 30 to 40, and 40 to 50. Well, they want midpoint, so between 0 and 10, it worked out nicely. They gave us the midpoint value on every single one of them. So our midpoints occur at 5, 15, 25, 35, and 45. And then to find the area for each of these rectangles, we take our interval times the function value at the midpoints. So our interval length was 10, but the y values, or the y values for these rectangles, the heights for these rectangles are, what's the y value at 5, at 15, 25, so on and so forth. Well, the y value at 5 is 14, at 15 it's 28, so on and so forth, and that's what we use as our f of x. We add the insides multiplied by 10 gives us 2,570. Now, before when we did derivatives it would be cubed, but now we're working backwards, so now rather than it being, we started with velocity, so now we're going to move downward, so that gives us our position, which is just going to be our units of feet. And lastly, it says use correct units to explain the meaning of this integral. Well, the velocity function in units is feet per second, but we're looking at the change in the velocity over time, so that's just seconds. If we simplify that, that's where it gives us feet, which is what we had on part A. So what this is really saying is the integral is representing the total feet the car traveled in 50 seconds. I hope that left-hand sums, right-hand sums, and midpoint Riemann sums at this point make a little more sense than just the foldable that we had started. In the next video, we'll be talking about the trapezoidal rule, which is also Riemann sums, but that's a more accurate form of finding the area under a curve.